Hey guys, and welcome back. So in this video, I'm going to give you some tips to help you solve polar problems, and then also talk about some interesting strategies you would use for problems involving polar area. So the first tip I wanted to give you is to watch for a negative radius. And we've seen some problems that have a negative radius, and they produce kind of pretty bizarre graphs. Watch for a negative radius. And what's going to happen is when you have a negative radius, this might mess up the bounds. It might make finding the bounds a little bit confusing. So, some of the things you want to think about when you have a problem that might have a negative radius is when I graph it on my calculator, does it go straight around from 0 to pi? Or does it have some kind of black magic in the middle? Does it go straight around from 0 to 2 pi? And so if your graph usually just goes right around like that, that's fine. But if the answer to this question is no, then in that case, you may have a negative radius in that case, or a negative r value. And then, of course, you could look at the equation and just ask yourself, like, is r ever negative? Okay. So let's give an example of what that might look like. So for example, here's a graph, and I'm just going to give you part of the graph. So here is r equals 2 minus 4 cosine of theta from 0 to pi. Okay, and I'm going to ask you to find the area in the third quadrant. Okay. So I'm going to give you a picture, but then we're going to go to the calculator. So when you graph this, the graph that it makes looks like this. It goes like that. So the area in the third quadrant that they're talking about is this little highlighted area down there in yellow. So what I wanted to show you is look what happens when you actually graph this on your calculator. So I'm in polar mode right now. So if I go to graph this, I'm going to graph 2 minus 4 cosine of theta. Okay, so now when you graph this function, I'm going to make sure, for my window, I only look not from 0 to 2 pi, but just from 0 to pi. And the reason I'm doing 0 to pi is because that's the values right there that I told you we're looking between. So look what happens when I graph the function. What we see is it starts down there like I did, and then it goes around. Well, that's interesting. Okay, so because you might look at this, and like obviously if you had to find this area, you would look at this and say, okay, well, obviously it's going to be 1/2 r squared. It's 1/2 times 2 minus 4 cosine theta squared. But the question that you have to ask yourself is, what are the bounds? And I think some people might see, oh, third quadrant. I'm just going to go from, pi to 3 pi over 2. But normally, when we have our third quadrant, that's like pi over on the left side, 3 pi over 2. But is that in the range we graphed? No, we only graphed the part of the function from 0 to pi. So one of the things that you can kind of do is look at this. So watch it graph on the calculator. And then ask yourself, where does it start? And we did that a little while ago, and we saw that it started, this bit right here, that happened when theta equals 0. So that was the starting point on our graph, when we're at that dot right there. Now, the question of where does it end? Well, okay, so we start at theta equals 0, and the graph went around, and that area in the third quadrant ends when I'm at the origin. So that's the end. So this area here ends at the origin. And of course, anytime you're at the origin, that means when your radius, your r value equals 0. So it ends when 2 minus 4 cosine of theta equals 0. So that means that cosine of theta equals 1/2. And theta is cosine, so that's the x value. So that's the first one over. So that's a pi over 3 and 5 pi over 3. Now, we don't care about the 5 pi over 3, of course, because we're just looking from 0 to pi in the problem. So what that means is when you look at this and you say, okay, I watch this graph. And again, if we let's just change a little thing so we can see a graph again. But if we start this again, we see it starts there at 0. Your graph goes in order. We told the graph to go from 0 to pi. So it started when theta equals 0, and it went around and ended up there at pi. So that was at 0, and then theta equals pi was still over here on the left side. So again, because it started with a negative radius, and if you plug in theta equals 0, you see your r is -2. It started at a negative radius, and then it's in quadrant 3 until it gets back here at the origin. when the r equals 0. So that's where this yellow section begins and ends, at 0 for my start and then at the end for my last. So my bounds here are going to be from 0 to pi over 3. And then, of course, you'll plug that in your calculator. Wesley's okay. We can say hi. Hey, guys. Wesley breaking the video. Okay. Good job, buddy. All right. I'm not going to edit that out, by the way. You have to watch that. So let's go on. Let's go on. So that's just an issue of what these problems are going to look like. If you see something weird like that, a lot of times the start and the end is when it goes through the origin when that r is equal to 0. So let me give you another case. So this is, of course, you plug in your calculator, and this is how you find that area, whatever that ends up being. We're going to do a similar problem now with an inner loop. So you have to find the area of an inner loop. And we saw one of these briefly on our assignment the other day. So suppose you have the graph of r equals 2 plus 5 cosine of theta. And I'll go ahead and draw you the picture. We'll graph it on our calculator in just a sec. But the graph that it looks like this. It goes, I don't know. Actually, I kind of lied in how I started that. But the graph looks like this. And what if I ask you to find the area of the inner loop? Now, as you can imagine, the inner loop is like this part right here. But let's watch our calculator graph this. So watch the calculator graph and see where it starts. Because where it starts, that's when your theta equals 0 is. So I'm going to graph this. This will be 2 plus 5 cosine of theta. And for my window, I'll just go from 0 to 2 pi so I can see all the way around. Okay. So when you have these inner loop problems, you say, okay, it started here at 0, and then it went over, and then back at 2 pi. Okay, so here's at 0, and then 2 pi. So somewhere between 0 and 2 pi, we had some weird black magic where it went across. And we see that's kind of at the origin. This kind of looks like an olive, I suppose, more than my graph does. But what you're going to do is you're going to say this loop, the loop starts when r switches from a positive value to a negative. That's when the graph kind of bends in on itself. And it ends when the r goes back to positive. So we start out at 0, we go around in this clockwise fashion, and then eventually we get back to the origin. And that's where we switch to a negative radius. So you can see kind of over here we don't have anything in the positive area, but that's where it switches to a negative radius. And then it gets back to a 0 radius there, and then it goes back around, has a positive radius until 2 pi. Okay, so what you're going to do to see where it switches from positive to negative, so this happens when the r equals 0. Because that's when that distance is 0. That's when you are at the actual origin. Okay, so how do we see when does r equal 0? Well, we have 2 plus 5 cosine of theta equals 0. This is not on the unit circle, but what I want to remind you is you can solve this on your calculator. And when you solve it, of course, you have to be in that function mode. As you guys have quickly seen, if you go to second calc, there's nothing there. There's no 0 or anything or intersect. But if you change your mode to be back in function mode here, now you can change your y equals to say, okay, here's 2 plus 5 cosine x. I'm going to change my window here to just go from 0 to 2 pi, because my x's are kind of like the thetas there. So we'll see, okay, there it goes positive to negative, and then it goes back negative to positive there. So we can find those two intersections here. There's zeros, because they're x-intercepts. So we'll go over here. Let's find the one on the right first. Okay, so there, whatever the right bound is, whatever the left bound is, I'll guess. Okay, so one of those where the r goes negative to positive is at 4.30087. So that's where r goes from a negative to positive. So what that means is that's where our upper loop or our inner loop ends. It ends at that 4.30087. Okay, and as for where it begins, we'll just do this again. So we'll go second calc 0 to find that. You can also like type in a bound, that kind of helps. So we have 1.5, and then we'll just like scroll over a little bit here. And that's going to tell you where the inner loop starts, because the inner loop is this region in here where your r is negative. That's where the loop is. So that's, I think, a key. The loop, that's when r is negative. That's your inner loop, and that's what we're looking for between those 2 points. So we see that loop begins and our upper bound there is theta equals 1.9823. Okay, so what that means is, so it starts theta equals 1.9823. So if we need to find my area of the inner loop, it's just going to be 1/2 integral of 2 plus 5 cos theta squared. Okay. And of course, the start of the loop is 1.9823. The end of the loop is 4.30087. Okay. Now again, it's 1/2 r squared because it is polar. So just as a reminder, when you're doing these integrals, you could do these integrals in either polar mode or regular mode. An integral is an integral, right? So put the 0.5 in front so you don't forget about it. And then we'll integrate the 2 plus 5 cosine of theta, or x. And that whole thing is squared. And then x goes from 1.9823 to 4.30087, whatever. Okay, so that tells us that this integral, this area, is 5.3803. And again, that calculates this yellow area, that inner loop, which is where I go through the origin, so my radius switches positive to negative. That's the key. Look where the radius switches positive to negative on these inner loops. Okay, cool. So let me give you just a couple other general tips. So some other tips for polar problem. You are only going to be in your calculator, you are only in polar mode to watch a function graph. That's the only time you really want to or even need to be in polar mode. And as you guys know, if you're going to be solving an equation, you must be in the function mode. Okay. Just some other tips. If you ever have a problem that says find a distance from the origin, anytime something is talking about a distance from the origin, remember they're just talking about r, the radius. That's the value they're looking for. And if they ever ask for a distance between two curves at an angle, you're going to see this on some of the review problems. Distance between two curves at an angle. Okay. So what that means is you have you have some outer curve here, you have some big R, you have some inner curve here, let's call it inner R. If you're trying to find that distance right there between them at some angle theta, this distance is what you're looking for, that's just the difference between the two. That distance, that theta, is just the outer radius minus the inner radius. And again, that should be similar to what we've seen before, because if you have a normal graph, right, you have f and you have g. If you want to find the distance between them, that distance there is just f minus g. Well, the distance between the two is just the outer minus inner. Okay, so that was some tips on polar problems, the inner loops. Thanks for watching, guys, and good luck. Have fun with the homework.